Well, hello, and on the bench today we have a little AM transmitter board which was kindly sent to me by a guy called Derek, who sells these on eBay, and I will try and put a link to this particular board. And he also has a shop selling other variations of AM transmitters, although strictly speaking he likes to call it an AM modulator because the power output is extremely low on this. So why would you want one of these? Now, before I get into that, what you get with it, you get the board, obviously you get a 3.5 to 3.5 millimeter stereo lead which you can plug into maybe a phone and maybe a CD player or maybe an old cassette Walkman. And you also get a circuit diagram which I'd already printed because he gave me a link, and I printed mine in black and white because I thought it would come out better on the camera when I go into it later. And you also get a basic description of it and how to use it, things you should and shouldn't do with it. So there you are, that's what you get with it, pretty comprehensive. And it is a really beautifully made board, can't fault the construction on there. It runs on a 9-volt battery, and as we shall see later, it takes very little current, so it would work for quite a long time. The only criticism I might have is that it would be nice to see a switch on this board so you could turn it off, on and off, rather than unplugging the battery. But that would be fairly easy to do. Also, if you wanted to, there's a couple of connections. You could run it on a power supply if you wanted to. But oh yeah, you get a piece of wire which is roughly 1 meter long, and it's just fallen out, which is not very helpful. And that will act as an aerial basically. And as I said, this is a very low powered board, so you won't get much range on it. You're not going to be expecting to get miles on it. You're going to get just a few feet. I'm going to screw that back in. I want it sticking out a bit, the metal, because I want to stick a scope probe on it. But anyway, so why would you want one of these? Well, certainly in the UK, if you tune across the medium wave band, there's less and less transmitters on there. They seem to be turning a lot of medium wave transmitters off in this country. Strangely enough, the Spanish seem to have taken over the medium wave. They've got a station on just about every frequency. Similarly, on long wave, I think in Western Europe now, BBC Radio 4 is really the only long wave station left. And how long that will last, I do not know. I know RTE in Ireland, that went off a few days ago. But this particular board is on 750 kilohertz on the medium wave, and you can see there it's marked with a little black dot. You can get different ones, you see, which he does to order. And 750 kilohertz. But that is not a normal channel on medium wave. In other words, it's not a 9 kilohertz preferred channel in the UK and Europe. That's not going to be a problem. If you're going to be using this really on an old radio, that's what it's intended for. Because with the advent of turning all these medium and long wave transmitters off, the old vintage radios that people have got are no longer going to be usable and basically redundant. So if you want to keep your old Roberts Hacker radio going, or your old Valve radio maybe, then this would be the perfect solution, because then you can just play your music through your old radio. So that's the basic introduction. So I think really the next step is to actually try it, and I'm not going to use this cable. I'm going to use a long one here, which is plugged into a music player. So I'll just set all that up and get back to you. So I'm all wired up now. I'm not using a 9-volt battery. I haven't got one. Decent one anyway. I wasn't going to go out and buy one because I'm too mean. So I'm running on my power supply, which is helpful because then I can monitor the current. If I go to the power supply, see 9 volts and it's drawing just 18 milliamps, which is a pretty low amount of current. So with your average alkaline battery, you're going to get quite a lot of use out of it. But as I said, you could run it on a power supply. But the perfect way to test it, of course, is by using this old radio. And this is not actually a very old radio. But it's probably the best oldish radio I've got. Roberts R900. Does medium, long wave, medium wave, and VHF. So we're tuned to 750, I think, and I'm going to start up the music, which is hideous, copyright safe YouTube music. Ah, dear. Okay, that's enough of that. I think that works very well. I think the audio quality is as good as you'd expect on a proper professional transmitter, which of course this is not. But as I said, it isn't very powerful. So you've got to get the wire pretty close to the receiver. You could extend the wire and they might give you a bit more range, probably would. You could also possibly put an earth wire on the board like a counterpoise, because there's an earth connection just there. That would improve it as well. But I can actually hear it on my receiver in the house, which has got a proper antenna up the garden, which is an active loop antenna, and that's 100 feet away from this little transmitter. So with a decent aerial, it will go, receiving aerial, you'll hear it a fair bit further than you will on a portable radio like this. So that I think is pretty good. that's enough of that. I proved it works, and it works very well. But what I'd like to go on to now is how this works. Sort of detailed description of how the whole circuit works. And I'll disconnect it for the time being. And unplug that. I don't need that at the moment. But what I will say about it, if we look at the back of the board, this is really hard to see. Where's my pointer? Right, on the back of the board we have 3 links. In the moment we've got the link there, and that's because it's set to 750 kilohertz at the moment, but there is provision via these links to have different frequencies, and I'll get into that later. I think, well, I'm certain one of them is 375 kilohertz. I don't think the average long-wave radio would go that high. But the other one might be more useful if you want to use it on long wave, is half of 375, which is 187 point something. Now it'd be just below radio 4. So that would be quite useful if you wanted to use this on long wave, unless you're very close to the radio 4 transmitter like I am. So yeah, I want to get into how this works now, so I'm just going to reconfigure myself. Okay, so what we've got here is we've got the frequency generator chip. Now uses a 12 megahertz crystal. You can use other crystals to obtain other frequencies. For instance, 10 megahertz would be one. And we've got a 4060, which I recognise because I've used them many times in the past. And that's the basic oscillator and divider, which divides down in 12 megahertz. We'll go over to the circuit diagram, which I've printed out. That's the generating bit, the 4060. So this particular chip has provision for an oscillator, and it's a, what do they call it, 14 stage ripple counter, I believe. Where's my cookbook? Where's my cookbook? CMOS cookbook. It's the only cookbook I use. Okay. 4060 binary ripple counter with internal oscillator. So what basically this has got in it, it's got lots of divide by 2s, up to with 14 divide by 2s. So whatever oscillating frequency you start out at is divided by 2, and then divided by 2, and so on, up to 14 stages of that. So the maximum division ratio is 16:4 on the final divider. And not all of the divisions are outputted. For instance, 248 and 2024, 2048 are not outputted. So you've got a limited number of divide by 2s, if you see what I mean. But it's a perfect application. So you're using this chip in this board. So I believe, let me see, the primary output that's connected at the moment, there are 3 options as I showed you on the board, is Q4, which will be 2 to the power of 4, 2 to the power 4. What's 2 to the power 4? I can't do that in my head. I can't do that in my head. I'm too tired. Let's see if I can do it on a calculator. Two to the power 4. Oh God, it doesn't like that. Where's to the power of? X to the Y? Yeah, could be X to the Y. 16, right, that makes sense, doesn't it? So, what that means is 12 exponent 6, 12 megahertz divided by 16, 750 kilohertz. So that works, doesn't it? That's how that one works. And what else have we got? We've got Q5, so that's 2 to the power of 5. Let's do that one. 2 power 5, 32. So 12 megahertz divided by 32, 375 kilohertz, which is, as I said, probably out of the top range of long wave. And the last one is Q6, that's on that output on the board. So that would be another divider up on the last one. So that would be 64, wouldn't it? So 12 megahertz divided by 64, 187.5, and well, 187.5 kilohertz. So that would work probably a long way. Okay, that explains all that. Throw the calculator away. But I've used this book over the years, especially when I was working. It was my go-to book when I was working with CMOS by Don Lancaster. And I tried to get a copy of this for years when I left work, and they were really, really expensive. I see this one is marked at $1. And I had to get it from America for slightly more than $1, but it's a really useful book. It tells you about everything about CMOS, but we won't get into all that today. CMOS logic chips. But so that explains the frequency generator. Okay, so now we have another familiar chip over here, which I've used many times, LM386, which is audio amplifier. I think it's got roughly 500 milliwatt, half a watt output, so ideal. And what happens is you plug your signal in here, doesn't matter if it's stereo or mono, and because the two stereo signals will be summed together with the 47 ohms here, and you have a mono signal coming in, because that's what you want. You can't do stereo on medium or long wave. And then that's amplified by the chip, and what we're looking for here is just a voltage swing which will modulate the transmitter. And come down here, we have the modulator and amplifier, which is a FET, and you take your drive signal, whatever one you've chosen, in this case 750 kilohertz, that goes in here and it drives this FET, creates a nice square wave probably here, because what comes out of here is a square wave basically, and that's not what you want to transmit. You want a more sinusoidal signal. So that comes into this transistor FET. Where's the FET? That's a little FET there. Doesn't need to be a big one, it's quite big enough. There's the LM386 modulating audio amplifier. Audio comes in there. There's also provision for connecting audio to these pins as well, if you don't want to use the socket. So back to all this, and where do we get to? So then your modulation comes in here from the audio output from the chip, and that goes through a 1 millihenry inductor just to give it some impedance, basically, at audio, because what we want is a swinging signal here that modulates the amplifier, RF amplifier. So after it's done all that, it's DC blocked through that 100 NF, and then quite critically here we have a pi matching section. It's called a pi, which you've got a capacitor on the input, inductor in series, and then capacitors down to earth on the output. So it resembles a pi, if you can get your head around that one. Now this is all quite critical, and not only does it match the impedance here to the output wire, it also has the properties of suppressing harmonics. But so that's how pi outputs work, and this has obviously been optimized for the piece of wire supplied with it. And if you wanted to connect a longer piece of wire to it, you're going to have to mess around with all these values to get a decent impedance match, because that piece of wire at 1 meter long is going to be quite a high impedance at 750 kilohertz. So this will not be a low impedance output at this point. And when I do my testing later on, I will be shoving it into a spectrum analyzer and completely mismatching this section, because I'll be loading it at 50 ohms, but at least it'll give me an idea of what it looks like on the spectrum analyzer. So there you go, that's how all that works. Any questions, pop them in the comment, because I've been doing this stuff for so long, I tend to find it hard to bring myself down to a level where somebody who doesn't know how this works can understand it, if you see what I mean. And anyway, all that just goes out to your piece of wire there, which is your 1 meter piece of wire. And as it says, you can change values, inductor values and capacitor values here to optimize your piece of wire you're using, if you want to try longer pieces of wire on it. So I think the next thing to do is to run it through a few technical tests, I'm not sure if that's the right, whatever, anyway. I think I'll put it on the scope first of all, and we'll have a look at the modulation. Get rid of my favourite cookbook and the calculator. Hopefully won't be needing those again. So I'll get the next bit set up. Okay, that's all set up. What I'm doing now is I'm running it on a signal generator into the input of the transmitter, 1 kilohertz, and with an amplitude of 12 millivolts, because it does seem very sensitive, the actual amplifier. And I'm monitoring on the scope, but at the moment if I can get this to stay stable, fairly stable. I've got no modulation at the moment, so this is just the carrier. So if we go out, we can see the 12 megahertz carrier. No, that's not right. I'm getting artifacts. I don't know why that says 9.5 8.9 hertz. That's rubbish. So you look down here, we're getting 750 kilohertz. I don't know if you can see that. So what's the point of that bloody stupid frequency counter on there? I don't know. But anyway, as you can see, that's the 750 kilohertz. Did I say 12 megahertz earlier? I don't know why I said that. But anyway, that's your 750 kilohertz. That's what's coming out of the aerial. So as you can see, that's a fairly good sine wave. Maybe a slight bit of distortion, but we'll look at that later on. But now if I turn the modulation on, which is 1 kilohertz, time base back down, we can now see that we've got a typical AM modulated carrier. It's very difficult to trigger on an AM signal, so that's why it's probably wobbling a bit. And if I turn the level up on the generator, you can see I've over-modulated it there, and I can turn it down. So that shows you a typical AM signal, because all these bits in here are 750 kilohertz, whereas the modulation is 1 kilohertz. And the other thing we can do is we can change the frequency. So if I go up to 2 kilohertz, it's still working fine. 3 kilohertz, 4, 5. So, you know, in theory, AM stations in this country are limited to 4.5 kilohertz frequency because of the 9 kilohertz spacing. So the best, highest audio you'll hear is 4.5 kilohertz. But this appears to go even higher than that. I mean, I'm at 6 kilohertz now, 7 kilohertz, 8, so on and so on and so on. So if you've got a really nice radio, in theory, depending on its IF filtering, you could get better sound than you would normally hear, if all that makes sense. Okay, that's the modulation for you. Turn the modulation off. Back to the carrier again. 750 kilohertz. Fine. Right, next thing to do with it, I'm going to test its frequency accuracy with a frequency counter. And all I need to do is disconnect my scope probe and plug it into my frequency counter. Frequency counter is up there, so thought I'd use the Raycall Dana today, and what that's telling me is it's 750 kilohertz 040. Dear. 750 040 hertz. So I'm quite impressed with that. That's telling me it's only 40 hertz high. That oscillator, 40 hertz high at 750 kilohertz, which is absolutely nothing. So that would be, you know, considering it's just a basic crystal oscillator, Derek's done his homework there and he's got it very, very close to perfect. That's what I say about that. Very good. I do like that frequency accuracy. Okay, next thing to do with it is put it on Spectrum Analyzer. Let's have a look at it on that. As I said, I'll be mismatching it then, because I'll be loading it. But there we go, can't be helped. So I've now wired it into my Spectrum Analyzer and center frequency 750 kilohertz. Fine. Let's press peak, and as we can see here, it's measuring minus 2.8 dBm. If it was minus 3 dBm, that would be half a milliwatt. Okay, half a milliwatt. I can actually do that on here. Units, watts, peak. Right, 525 microwatts. That's fine. Let's put it back to dBm. I prefer dBm. So, not a very big signal, but as I said before, I'm mismatching it by loading it at 50 ohms. So it's probably producing more than that into that piece of wire. So, no modulation at the moment, that's just your pure carrier. So we could look at the harmonics. I increase the span. Aperture, frequency. Right, that's your 750 there, 750 kilohertz. That's your second harmonic. We can do marker, delta marker. So if I go and look at this one over here, that's the second harmonic. It's some 51 kilohertz away from the fundamental, it's telling me, and it's only 15 dB down on the fundamental, which is not great as far as harmonics go, but as I said, I'm mismatching it to start with, and as Derek says, you don't expect perfect harmonic rejection with something like this. It's not a professional transmitter, let's face it. So that's quite acceptable because of the power levels you're transmitting. 15 dB down from half a milliwatt is bugger all, basically. And if I wanted to, I can even look at the other harmonics. Span. There, okay, there's all the other harmonics. That'll be a third harmonic, fourth, fifth, sixth, up to infinity, basically. But that's what you'd expect to see, without more filtering. But perfectly acceptable, as far as I can see. Let's go back to 750 kilohertz. And marker, normal marker. What I want to do now is apply some modulation at 1 kilohertz and we'll look at it. Better turn the frequency counter off, don't need that anymore. So let's turn this 1 kilohertz signal on. And we got a lot of wobbling because we're now modulating it. And if I reduce the span, we can actually start to see the sidebands. So that's your carrier, the 750 kilohertz, and that's just upper sideband and lower sideband that's being generated when you modulate with 1 kilohertz. So if I do right peak, where's right peak gone? Next peak? Alright, next peak then, if you like. That's telling me the lower sideband is 749 kilohertz because you're modulating with 1 kilohertz, and this one again will be 1 kilohertz away from the center carrier. Now the other ones down here, we don't want to worry about those. That's to do with intermodulation distortion, which I won't get into but what we're really not interested in these things at all. They're not a problem. They're massively down anyway in dB terms, so they're not significant in this application. But if I change the modulating frequency, let me move that a bit. Let's go to 2 kilohertz. And we can see now that the two sidebands have moved, so they're now spaced 2 kilohertz away from the carrier. And if I might want to do this, and so I've got more span, so I can show higher frequencies. Go to 3 kilohertz, and they're now spaced 3 kilohertz, but they're still staying at the same level in relation to the carrier. 4 kilohertz. No, it's actually 5 kilohertz. And as I said, they're not diminishing significantly, so it's capable of transmitting audio to at least 6 kilohertz. That's what I'm trying to explain. So there you go. That's what an AM signal looks like on a spectrum analyzer. Of course, it would look a lot worse than that. If you put audio on it, it'd be all sorts of rubbish across the screen. Do I want to do that? Probably not. Not on this particular test. But that just shows you what an AM signal looks like on a spectrum analyzer. That's enough of that then. What else can I do now? I think what I'd like to do, I was talking about these particular links where you can select different frequencies. I think what I'd like to try is see if it works on 375 on my radio, and if it doesn't work on 375, it's bound to work on 187. See how it sounds on there. So I'll go ahead and warm the soldering iron up and get back to you. Okay, just one final look at the spectrum analyzer. I've now got music going into it, modulating it as you would do normally. And come on, I want some music. There it goes again, that's better. So this is what it looks like on a spectrum analyzer with an AM modulated signal with music on it. And as I'm on a span of 20 kilohertz, from the carrier to here is 10 kilohertz. So you can see there is audio information going all the way up to 10 kilohertz basically. But it isn't filtered. It's not designed to be filtered like a proper professional transmitter would be. Anyway, that's enough of that. Well, I tried it on 375 kilohertz and the radio wouldn't tune that low, high. So this is on 187. But it is very weak. That tells me that the circuit is optimized for what it should be on, 750 kilohertz. And you need to mess around with this tuning circuit to get it to work on long wave. But at least I prove it is possible to do it. It's just very, very weak. It does work, so I proved it will work. Okay, well, I think that's more or less the end of it all my testing, and very, very interesting little project, and quite impressed with this. So if you want to buy one, I'll try and put a link in to the description on eBay, and maybe Derek will sell a few more of them after people have watched my videos, who knows. So thanks for watching. Bye for now.